Log on, tune in, find out. Another good idea from Cambridge.
I should explain where I fit into things. I joined the mathematical laboratory in 1956. At the time, I was a research student in the Cavendish. Would you believe it? Researching the propagation of radio waves in the ionosphere under the direction of J.A. Radcliffe. My supervisor, in one of our early meetings, said, "Why don't you go down to the maths lab and see if the computer can help?" Now, there's a throwaway remark which changed my life forever. And one of the small number of remaining people who programmed the EDSAC, there are a number of them sitting amongst the audience, I'm equally one of the small number of people who attended lectures in the old anatomy lecture theatre. And this picture shows on the right the entrance to the lecture theatre, which of course Maurice later commandeered to accommodate the Titan. And on the left is the door. You can't quite make it out. It says mathematical laboratory. Not that door, that was the front door. This was the back door into the courtyard. And many occasions I walked past that door which said mathematical laboratory and ignored it and went to attend my lecture. But when my supervisor said, "Go and see if you can help," I went in through that door, and that was the start of a new career. Maurice must have recognized some enthusiasm and perhaps had some sympathy for someone researching radio waves in the ionosphere. And so he offered me a desk in the laboratory, and I stayed there for the next 11 years. By the time I got there, the EDSAC was near the end of its life. The computing service it offered was running like a well-oiled machine, or as well-oiled as you can be with 3,000 thermodynamic valves, and it was running more or less 24 hours a day. A night shift was defined as until the machine dies. And as soon as the EDSAC 2 came into operation in '58, I started using it. A salutary experience, I repeated a year's calculations on the EDSAC 1 in about a week on the EDSAC 2, just to make sure my program still worked. Then Maurice actually appointed me to the staff. It will seem strange to a modern audience, but there were no job descriptions in those days. It was a general suggestion I should make myself useful and help David Wheeler. So I did, to the extent that towards the end of my EDSAC career, I was writing bits of microprogram and bits of the reserve memory, the fixed store. So that's my background. Now, as Martin has said, Maurice liked using computers as well as making them, and he designed the EDSAC with a view to making it usable by the physics community. And after just a year, he was quite clear it was working as he'd expected, and so in 1960, he started thinking about the successor. It was clear we needed a bigger, better EDSAC. Not something new of a different design, but a bigger, better EDSAC. And surprisingly, a year later, in '51, he attended a conference and outlined his design. A parallel machine, bit-sliced architecture, driven by a microprogram. 1951. You say, sort of, gosh. He talked about the design with his colleagues, particularly Bill Rennick, and they rapidly realized that the problem would be the memory, because there were two technologies available, the mercury tubes, which had been used in the EDSAC-1, and the Williams CRT store, which was used in the Manchester Mark I. Maurice, in his account of the EDSAC-2, says that he rejected the Williams store because it was difficult to get cathode ray tubes of sufficient quality. But I suspect, knowing Maurice, that the Made in Manchester label that came with it might have just influenced him ever so slightly. There probably aren't a lot of people present who remember the book by Fred Brooks called The Mythical Man Month, the first and best book on software engineering. Fred had developed the software for the IBM 360 and set down his experiences on this bed of nails in his book. And one particular thing he draws attention to is the second system effect. At the time, then, and indeed for probably even now, in IBM, the ethos was that at the appointed date for the end of a project, you declared a success, and you were then moved on to another project. And Fred pointed out that if you gave a designer a chance to have a second go at his project, the results were always very good indeed. And the EDSAC-2 is the ultimate second system because it was designed as a bigger, better EDSAC. The parallel arithmetic design was straightforward. They were stuck with mercury tubes, so they started detailed design on that basis. But Maurice, with his optimism, remarks that we knew the mercury tubes weren't ideal, and we thought something better would turn up. And indeed it did, because he went to MIT. He was always going to MIT, and he always came back with a good idea. And he came back from that visit having seen the core store going into the Whirlwind computer. And that clicked. Core store was the way to go. This is characteristic of Maurice. He could recognize a promising idea or technology and pick it up running, and equally he was quite ruthless in dropping an unsuccessful approach. So all that work on the mercury tubes went to the bin, and they started designing the magnetic store. One of my first memories of the EDSAC-2 was seeing the core store being, I think the word is woven. It was a 40-bit memory, so there were 40 planes of 1,024 cores, 3.5 millimeters, and in front of those was an array of bigger cores to actually do the driving. There was a wire which went through each line of bits in the core store, wound round each core the right number of times. There was another wire which went through in the other direction, wound through the core a certain number of times for the readout, and a third wire going through because you had to write the memory back. The process of reading turned everything to a zero, so you had to write back the ones. So there were threading 3 wires around a 3.5 millimeter core, and not surprisingly, the job was given to young ladies with acute eyesight and a skill in needlework. That store, it was a different technology from MIT. Maurice wanted to adopt the MIT technology, but Bill Rennick thought he had a better idea, and it was characteristic of Maurice that if he'd appointed somebody, he trusted them, and so he let Bill go ahead with the alternative design. Not only was it 1,024 40-bit words, they put on what they called the reserved store, 768 words of read-only memory in the 1950s. And this was, I think, a Wheeler idea because he wanted all the system software to be available in that reserve store so that people didn't have to waste space in the big core store with instructions, and also didn't have the bother of physically assembling subroutines into an input tape. So the core store was going ahead. The arithmetic unit, the bit slice, again was fairly straightforward. You've got a 40-bit arithmetic unit, 40 identical chassis, each of which contains 1 bit of each register, 1 bit of each adder, 1 bit of each shifting register, and these go into a frame. You can see there Sid Barton inserting a bit slice. It's about that long, and you can just about pick it up with 2 hands. It's a posed photograph, but I know he was inserting it because he's got his hand underneath the front end. When you pulled a chassis out of the machine that had been on for hours and hours, it was too hot to touch. You got it out and let go, so it was certainly faulty by the time it hit the deck, even if it hadn't been faulty when it started. And the way things worked was that the engineers obviously knew how to mend the machine, but because of the architecture, someone like me, who didn't know any electronics, could fix faults, because round the back, as well as the back wiring, which linked the various chassis, up at the top, there was that board of neons, which displayed the contents of all the important registers. There were the 40-bit arithmetic registers, then the small panel underneath of the 11-bit control registers. And if you knew the logical design, you could run a test program, stand there watching the pattern of the lights, and deduce which chassis was faulty. Having done that, power the machine down, get the chassis out and drop it, go to the pile of known working chassis, slide it in, screw it in firmly, power up, and if you were lucky, the machine was working again. The chassis that you pulled out were retrieved next morning by the engineers, and they had a test rig so they could be repaired offline and then returned to the pile of known good. So that was a successful architecture. The core store and the reserve store were there. The remaining thing was the control of the program. Now, if you've actually read the details of the EDSAC-1 architecture and its control mechanisms, you will rapidly realize why Maurice invented microprogramming, because the control of the EDSAC-1 was fearsomely complicated. The idea of the microprogram is you have a matrix, again, of 1,024 cores, and each core, when it's fired, controls one or more gates in the arithmetic unit or the control unit. So each gate has a wire which is then threaded through each of the cores that has to fire it. Again, the right number of turns, and within that there's microcode which decodes an instruction, finds the address, operates the memory to extract the operand, and then fires a sequence of cores to open the gates that are required to be opened for that operation. So there's yet another winding going around that core which determines the next gate in sequence to be opened. Programs need conditionals. That was something that had been discovered very early on. And so the microprogram provided conditional operations, both two-way and four-way, that although the cores were all physically separate, the logic was such that in one position you had 2 or 4 virtual cores, and you selected which one of those was going to fire. In this picture, you can see around the side the various chassis controlling the microprogram. What you can't see is the whole lot, that matrix of cores is embedded in araldite. Now, you think of araldite as an adhesive, you know, sticking on Spitfire's wings and the like, or mending the broken pots in the house, but it's an incredibly tough substance. You could make roads from it, but you'd never be able to get down onto the cables. And that was a major problem, of course, with the microprogram. That once that araldite had been poured, that was it. You couldn't change it. When I actually graduated to writing bits of microprogram, I made a mistake. So, what did we do? We changed the manual. Maurice's pragmatism to the fore. What are you going to do about this, David? I don't know. Easy, he said. We'll change the manual. So for that instruction in the programmer's manual, there was a little footnote which said, please note that after obeying these instructions, you must add 9 to the instruction counter. So, this is a very rushed presentation, I'm afraid. You know, I could go on all afternoon. But just to round off, when we started using EDSAC2, 1,024 words of 40 bits, that's 2 instructions per word, seemed immense, almost infinite horizon. But of course, as we got more ambitious with our programs, the memory became increasingly a problem. So Maurice, he couldn't actually buy a large memory, but he set about thinking how it could be integrated into the EDSAC2. And of course, he had a problem because there were no spare address bits. The instruction could address either one of 1,024 words of the main store or one of 768 from the reserve store, but that was it. So Maurice played around with ideas for indirect addressing, passed these ideas over to David Wheeler. Well, this problem, how do you squash some extra bits into an instruction when there's no space? That was meat and drink to David. And he came up with a fiendishly ingenious scheme which allowed you to partition the hypothetical large memory by having 128 base addresses at the bottom, and out of the fully used bits in the address structure, he managed to select one of those 128 and then provide an offset of up to 1,024 on top of that. Luckily at this stage, a 16K solid-state memory came on the market. So again, Maurice's view, something will turn up, had been perfectly justified. Ampex provided the memory. We installed it. The users found it a bit difficult to get by because it may have been obvious to David Wheeler and probably to Maurice how easy it was to use it, but it wasn't the same to them. So in pursuit of my brief of making myself useful, I wrote an assembler which hid all the gory details. And from then on, we had the 16K memory. There's a picture of the EDSAC2. Right at the front is the control console, you might describe it. The machine itself is on the left. The magnetic tapes are over on the right. There's another picture of it. This was the mid-morning program test opportunity. David Wheeler called it the EDSAC operating system because you stood in the queue. When you got to the front, you put your program into the paper tape readers, which are on the left there. run your program, and the paper tape output punch on which your results came was cunningly situated at the far end of the room. So you walked to the far end of the room to get your tape, and then at that same far end of the room, you went to a teleprinter to print out the results. An exact model of an operating system, except only one user at once. That is as much as I've got time for on the EDSAC 2. Let me just say a very brief word about its successor, because by 1960, it was clear that we needed an even bigger and even better EDSAC, and the waters were muddied by the government deciding to provide a computer for every university. So Brian Flower's committee decided which computer we were going to have. Of course, academic freedom means you can't tell a university what computer it's going to have. You tell it how much money it can spend. And when you look at the manufacturer's catalogues, you find there's only one machine that you can afford. In our case, it was a KDF-9 from English Electric. Nobody liked this idea. Maurice sent David Wheeler and myself up to Kidsgrove to have a look over the KDF-9. We came back and said we'd be better off keeping the EDSAC. So Maurice then went on to another thing he did very well, exploring his contacts. And amongst those, he contacted Peter Hall, who was the managing director of Ferranti in Manchester. And Ferranti were planning a baby atlas. And Peter Hall came up with a scheme. He said, we'll sell you at factory price the basic components. You commission them, design and build the various bits to put them together, and then hand over the rights to this machine to us. There was born the Titan, but of course that's David Hartley's story to take over.